Okay, so I'm going to do, in these 4 problems, this is basically every kind of type of problem that you could see, just about. All right, so they're going to start out with some kind of shaded region. You can see the question starts out, let R be the region enclosed by the graphs of f of x equals x minus 1 squared. That's that parabola. And then g of x equals 1 minus x, as shown in the figure. Okay, so we just got that. Okay. All right, next it says region R is the base of a solid. So that shaded region is just where the base of some solid's going to go, and then the actual solid's going to kind of come out of the paper screen. Okay, find the following volumes according to the description of each cross section. Okay, so for all these, it's a good idea to draw a picture. So we can kind of take this picture and focus on that. Okay, for these types, I think the best thing is to start with the general kind of formula. So you always do an integral, and you always integrate some area function. And this is the area of the cross section that they're describing. All right, for this one also, we know that this shaded region here goes from 0 to 1 in the x direction. And that'll be our limits here. Oops. Okay, I should say too, with these, if it's perpendicular to the x-axis, everything in here will be in terms of x. So this area function will be in terms of x, and these limits are these x values here. Later on, or sometimes if it's, for other problems, if it's perpendicular to the y-axis, we would be using like these y values as the limits, and then we'd have to get these functions in terms of y, x equals something in terms of y. Okay, so we start here. We got the limit, and we know it's some area function. So since this is a square and it's perpendicular to the x-axis, so think about if we just draw that. So we know like the square will like come out of the paper, and technically there's an infinite number of squares. This. But the fact that mostly all you really need is like this would be like the base of the square, that little line. So really just kind of draw that line. Okay, and then actually I probably should have started with this. So this area function, since it's a square, first call it s squared. Side length squared. So like for this one, this is s. That's the side length of one of the square cross sections. So get this in terms of x. All right, and the way to get if you have this distance is like the distance between the vertical distance between two graphs is just the top minus the bottom. So that is just 1 minus x minus x minus 1 squared. Okay. And so for this one, that's it. It's like the whole problem. So now we got the side length here, that's s, and so just substitute it for this s here. Right, so s squared, and that's what this is, s, and then the whole thing squared. All right, and that's as far as I'll go. Just want to see how to set this up. From here, this is just evaluating a definite integral. So I'm going to skip that part just for the sake of time. All right, but that would be the answer once you evaluate that integral. Okay, next one. let's do the same thing. We'll have a drawing. Take this. Okay, for the next one, we're trying to find the volume where, so find the volumes according to the description that cross sections are rectangles and they're perpendicular to the y-axis and the height is twice the base. Okay, so what they're saying is you're going to have like, so now that is going to be the base of a rectangle, and the rectangle is going to be, the height is going to be like twice as high as the base always. Okay, let's get that area function first. Okay, so it's a rectangle, so it's base times height. But in this case, the height is twice the base. So that height is really twice the base. And so really this would be 2b squared. All right, so we got to really get what that base is. So let's ignore the whole thing and just focus on the base. That's in the, just that line. Whoops. Okay. All right, so that base, actually let me erase that one. It's kind of weird. All right, so same thing where like in this one, that vertical distance is the subtraction of the two functions. Same thing here, horizontal function or horizontal distance between two functions is you subtract them, and you always do right minus left. But these have to be in terms of y, so we'll just have to rewrite these. Okay, so the g of x is really y, right? So this will really be, get this. Okay, so instead of, so this is really 1 minus x. That means x equals 1 minus y. Okay, so this will be the function that we use. So that's in terms of y. Right, you have x equals something in terms of y. Okay, if we do the same thing with the other one, so you know that f of x is y, so we'll square root both sides. So square root of y. So actually, technically, it's plus minus square root of y, and then plus 1. All right, but this is the left-hand side of the problem, so that's really, we're going to choose the negative part. So it's really negative y plus 1, and I'm going to rewrite it. X equals 1 minus y. That should be a square root too. I don't know why I forgot that square root. So it should have been plus or minus square root of y, and then we realize it's negative square root of y. Okay, so again, that'll be the function we use. All right, for our integral, we know the shaded region, so everything's going to be in terms of y since it's perpendicular to the y-axis, this cross section. And then we'll, our limits are going to go from 0 to 1, so this is along the y. And then we're going to get some area function, area of that cross section. Okay, and then, so we know the area is 2b squared. And actually, sorry, this will be not in terms of x, this will be in terms of y. So let me fix this. Okay, so now we have to get this b in terms of y. So this distance is really b. That's the base of the rectangle. And then that distance is just these two subtracted, but it's right minus left. And so that b is right minus left. And that's it. And then you just substitute it into the, instead of 2b squared, it'll be 2 times 1 minus y minus y squared dy. All right, and then again, we could evaluate that, but just for the sake of time, I'll skip that. So whatever that is, that would be the volume of this solid that they described. Okay, next one. So let's grab this one of these pictures. Okay, so now cross sections are equilateral triangles and they're perpendicular to the x-axis. Okay, perpendicular x-axis means everything's going to be in terms of x, so we can deal with these functions as they're written. Okay, so we'll start off with, we know it's going to go from 0 to 1, because that's where the shaded region goes from and to in terms of x. Start out with some area function. Okay, so equilateral triangles that are perpendicular to the x-axis. Okay, so that'll be like the base of some equilateral triangle, and then it'll just be like that. Okay, and that distance, the distance between those is the base, or is the side length. So yeah, it's really like a side length. So let's call that S. All right, and then the formula for the area of an equilateral triangle. S squared root 3 over 4. Okay, and then we know that S, in this case, is the distance between those, which is the top function minus the bottom function. Okay, and then S squared means it's just this whole thing squared, and so this will get replaced for this x squared here. And so when we do this integral, okay, so S squared is that big long thing. And it times root 3 over 4 dx. And that's it. Okay, so don't, not to say these are always the easiest, but you can see, like, when you kind of know how these work, they don't take a lot of work to them, but there is a lot of understanding though. Okay, and then the last one, let's grab a picture. Oops. Okay, semicircles perpendicular to the y-axis. Okay, so start off 0 to 1. Okay, and that's because since we're looking at cross sections perpendicular to the y-axis, we're looking at these y values. So this region goes from 0 all the way to 1. So okay, and then also, since it's in terms of perpendicular to the y-axis, this will be all in terms of y. Okay, so we look at this distance. That'll be the subtraction of the two, and we'll see how it relates to this, to the area of a semicircle. All right, so area of a semicircle is half the area of a circle, so half pi r squared. All right, so this one's a little different because, before in the other ones, this distance between the functions, which is just the subtraction of the two functions, was like a whole side length of the previous figures. But now if it's a semicircle, that distance is a diameter, but the formula needs a radius, So the radius of this is really half. The radius of this semicircle is really half the diameter, so it's half of whatever we get when we subtract these two functions. Okay, and that radius also has to be in terms of y, so we got to get these functions in terms of y. And we already did that before, so I'll just rewrite them. So this is really x equals 1 minus y, and this was x equals 1 minus square root of y. Okay, so that means that radius is the right one, 1 minus y, minus the left one, 1 minus root y. All right, and then now just plug this, whatever this radius is, just substitute it in for r. And then we'll take this whole area function and substitute it in for the area here. So our whole thing, 0 to 1, is going to be 1/2 pi times that radius, or that kind of expression that represents the radius, squared dy. All right, and then whatever that integral is, that'll be the volume. So these are all volumes. So that would be a volume of that whole shape that has those as cross sections. Okay, the last problems were problems where they describe the volume by describe the volume by really just describing the cross sections that you'd get for that volume, for that solid. Okay, these are going to be volumes that you get by taking some shaded region and rotating it around a horizontal or vertical line. Okay, usually if it's a horizontal line, it'll be the x-axis. So x-axis horizontal line, and stuff that the x-axis and horizontal lines kind of work the same way. Because anytime you're rotating around the x-axis or a line parallel to the x-axis, any other horizontal line, these are always going to be in terms of x. If you rotate the region around the y-axis or something parallel to the y-axis, another vertical line, then your integral has to be in terms of y. Okay, so these first two will be in terms of x, and these two down here will be in terms of y. Okay, but not much different besides that. Okay, so this talks about that region R is the region enclosed by the x and y axis and the graph of 1 minus x squared. Okay, so just that. So you can see the y-axis, the x-axis, and the function enclose this area. Okay, so for each of these, we'll find the volume of the solid generated when R, that shaded region, is rotated about. So we'll start off with the x-axis. Okay, and actually I'll do that for each one of these. We're going to have a picture for each one. So when you rotate these around the x-axis, really cross sections are circles. So technically this is the same type of problem as the previous one, but they're always circles. So area circle is pi r squared, and so these will always be some kind of integral from a to b of r squared, pi r squared. For this one, this will be in terms of x, so I'll have a dx there. All right, and then if we look at the figure, if this thing gets rotated around the y-axis, sorry, around the x-axis, it's getting rotated around. Then really, like, if you look at, let's take a little line here. So like this will get rotated down here, and it'll form like some kind of circle. So that's like the cross section. That's one cross section that you'd get when you rotate this region. Okay, and then this, so that's the radius of that cross section. And so when you're dealing with the distance, so this distance is the distance from the x-axis to the actual function, which is just the function. So just get used to that. When you go from one of the axes to the function, that will get represented just by the function itself. So that distance is 1 minus x squared. Same thing if it was horizontal distance. It would be the function, but the function would have to be in terms of y. And so that's it really for these. So you really just have to find that radius, which is just that distance. And then you just look at the limits. So in terms of x, this shaded region goes from as far left as 0 and as far right as 1. And then it's that radius, which is the function squared, and that's it. So that would be the volume of that shaded region. Okay, so a couple things. So for this one, this is called disk method. Doesn't matter what the name of it is, but it's called disk method. Notice how you were rotating around the x-axis, and this shaded region, there was no gaps in between the x-axis and the shaded region. We'll see for some of these there'll be gaps where there's like no shaded area touching the axis that you're rotating around. Yeah, so that's something to pay attention to. So kind of the main things to pay attention to is, are you rotating it around the x-axis or something parallel to the x-axis? Because then everything has to be in terms of x. And then, or are you rotating around the y-axis or something parallel to the y-axis? And then everything has to be in terms of y. So that's one thing. So what are you rotating it around? A vertical line or a horizontal line? And then the other thing to pay attention to is if there's any gaps. And we're going to do those a little different. So, okay, so let's look at the next one. Okay, so now we're going to rotate this around the horizontal line y equals 2. Okay, so we're rotating it around this line here. All right, so notice now a couple things. So first off, that line of rotation is above this shaded region. So that's one thing to pay attention to. Also, this is like what I was talking about, where there's a gap in between the shaded region and the line. There's all this space. Okay, so this is called washer method. Okay, so whenever there's space between the axis of rotation and the function and the shaded region, this is called washer method. And so the formula for washer method, almost the same thing, pi, and then it's big R squared minus little r squared. And this will be dx or dy. For us, this will be dx since we're rotating around a horizontal line, parallel to the x-axis. Okay, so I don't know if you can picture, but when you rotate this shaded region around this line, this will be like the outer part of the thing that gets rotated, and this will be the inner part of the solid that's formed. This will be the outside, and this will be the inside. Because when you rotate this, there's going to be a hollowed out section. This will be the outside of that hollowed part. This will be the inside. Okay, and so the big R in the formula represents the outer part, the outer radius, and the little r represents the inner radius. So this outer radius is always bigger than the inner radius. Okay, so the outer radius is going to get be when you take this line that's farthest away and just rotate this outside line about the axis of rotation. So think about this distance here. That distance is the outer radius. So notice that doesn't change, This distance for the whole function is always 2. So really big R is just 2. Okay, let me erase these. Okay, little r, we're going to get when you rotate the inner part about that line. So really just draw a line from the inner part to the axis of rotation. Okay, so I don't know if you've done work with this. So think about this distance here is the function. That's 1 minus x squared. Actually, let me write that. Okay, this distance here is 1 minus x squared. And then think about this whole thing is 2 always, and this is 1 minus x squared. So the rest is going to be 2 minus 1 minus x squared. Okay, the thing to learn from this, so you can go quicker in the future, is notice that it's the axis of rotation. That was y equals 2. It's always the axis of rotation minus the function. And that's only if the axis of rotation is above the shaded region. If the axis of rotation was below the shaded region, it would be the function minus the axis of rotation. So these two would just be switched. Okay, so in this case, the inner radius is 2 minus 1 minus x squared. Okay, and then the, so we got, kind of only have to get really 3 things. We got big R is 2. We got little r, 2 minus 1 minus x squared. And then the limits, last thing to get, just go from 0 to 1, just for the shaded region. So this whole volume is pi, and I'll go from 0 to 1. So big R squared is just 2 squared, little r, that. And then this whole thing, we'll just put a dx there. And that's it. So that would be that volume. Okay, so the next one, oh, oops, I lost track of this. All right, that's good enough. So this next one says, so we're going to rotate this around the y-axis. Okay, since we're rotating on the y-axis, so we're going to really look at just a horizontal line that'll kind of represent the radius. All right, and since, rotating around the y-axis or something parallel to the y-axis, you have to get this in terms of x. So and then just start solving for x. Okay, and technically it's plus and minus, when you square root, when you square root both sides. But this is the plus part, and this would be the minus part. So it's just plus. Okay, and then also, since there's no gap, we're rotating it this way, and so we'd be looking at the gap on the left. And since there's no gap between the axis of rotation and the shaded region, then this is going to be washer. So we'll just use that simple formula. Just that formula there. Okay, and then here, since it goes from axis of rotation, or from the y-axis to the function, that's just the radius here. That's like big R here. Okay, so really this is big R, and we just substitute it. And so that'll be pi integral, and then we look on the y-axis, this goes from 0, this shaded region goes from 0 to 1. So those are our limits. And then it's the square root minus y squared. Okay, and then I won't solve this, but definitely we'd simplify this. All right, and then evaluating that would be that volume. Okay, last one. Grab this. I don't know what happened to that. Okay, so now we're gonna rotate it around a vertical line. Oh, that should be x equals -1. That's what I meant to do. Wait, x equals, yeah, let's do, wait, sorry. I meant that to be to the left. This should be -1. So x equals -1. All right, so we're going to rotate it around this vertical line here. Okay, so now since there's a gap in here between the shaded region and the axis of rotation, that means we're going to be using this formula. Okay, and then since we're rotating it around something parallel to the y-axis, this will be in terms of y. Okay, so when you rotate this, if you think about it, this whole thing's getting rotated, so this would be the outer part, and this would be the inner part. And so we need this outer radius, and then the inner radius. So real quick, so this distance from the axis of rotation to that line, that's changing, so as you go down the function, that's this is going to change, and so this will be a function of y, and so we already know that x equals square root of, what was it, 1 minus y. Okay, and then this will be the big R. And then the other distance from the axis of rotation to the nearer part of that shaded region, that's not changing. That's always 1. So really little r is 1. All right, that's it. And then we just substitute this. Okay, and then we look, this is in terms of y, so we're looking, the shaded region goes from 0 to 1 in the y direction. And then big R squared is that square root squared, so that square root will cancel out. And then minus 1 squared, which is 1. That's it. And just evaluating that would give you that volume. Okay, so now you can see, so you see the two problems where you have gaps. That's when you use these formulas here. And then when you rotate around either the x-axis or something parallel to the x-axis, it'll be in terms of x. When you rotate around the y-axis or something parallel to the y-axis, it'll be in terms of y. And then just getting radiuses. If the line's above, if the line's either above or to the right, then you'll do the line. Oh, I made a mistake. God damn it. All right, I'm too tired to edit this, so I'm just going to tell you I made a mistake and then tell you what it was and fix it. All right, so this radius isn't just the function, it's the function plus 1. So then really, so that's not big R. So big R is 1 plus that function. Okay. Okay, so let me fix this. So that bigger radius gets squared. Doesn't matter what it is. This would be a calculator question if they asked, probably, I think. Maybe not. And then minus the inner radius squared dy. Okay, so that would be it. Okay, so notice what happened was, what we really did. So if the axis of rotation, so look at these two. So if the axis of rotation is either above or if it was to the right, you would do the axis of rotation minus the function. And that's like what we did for this one. We did axis of rotation 2 and then minus the function to get the radius. Okay. But if the line is below or to the left, like in this case, down here, you do the function minus the axis of rotation, so you do the opposite. Okay, so the one above, you do axis of rotation minus function. Here you do function minus axis of rotation. Okay, and that's what we did. We did function, so if you do minus a -1, that's really +1, and that's the way we got that. Okay, and that's everything.